First of all, a big thank you to the organizers for putting this together and giving me this opportunity to share these results. This is recently completed work that you can find on the archive with my co-authors listed here. And we're looking into internal Faraday rotation, how that reflects the state of the black hole accretion flow. So as I'm sure you've all seen, the Event Horizon Telescope has resolved the accretion flow around the black hole at the center of M87 star. This is an image for one particular day, April 11th. And in order to interpret this image, the collaboration created a library of general relativistic magnetohydrodynamic or GRMHD models, as well as their ray traced images to span three main parameters to see what we could learn about this accretion flow. So the first is the magnetic field configuration, whether it's MAD or SANE. The best acronyms in astronomy, as far as I know. Magnetically arrested disk has a strong enough magnetic field to affect the dynamics of the accretion, whereas in a standard and normal evolution picture, a weak and turbulent magnetic field goes with the flow. Black hole spin is described by this dimensionless spin parameter going from 0 to 1, where 0 is Schwarzschild and 1 is a maximally spinning Kerr black hole. And then a negative value of the spin means that the disk is retrograde with respect to the black hole. And then finally, this final parameter is called R high. That's one particular parameterization of the electron temperature, where here is that R high is the ratio of ion to electron temperatures in large beta regions. So larger values of R high is going to typically cool down the midplane. And so with combined multi-wavelength constraints, as well as this image, this work ruled out about half of the models that were probed in this library, including all of the non-spinning ones. But so far, this is based on the just total intensity image that is shown here, when in fact polarized measurements were taken and have not yet been published. So it behooves us to better understand what we can expect from polarimetry and how that reflects the state of the accretion flow. We expect that polarization is going to tell us a lot, because in the millimeter, what we observe is synchrotron emission, and that has an intrinsic linear polarization fraction that's near unity. And the magnetic field geometry is imprinted on the linear polarization ticks. When a synchrotron emitted photon is created, it's perpendicular to both the local magnetic fields and the photon wave vector. And so this is one way in which that gets imprinted on a linear polarized image from modeling. This is Palumbo, Wang, and Prather 2020. And they show that these MADs may have a more twisty polarization pattern than the same. If you look at these blurred images, which are similar to EHT resolution, you can see the whirly pattern in the MAD simulation, whereas the SANE looks more radial. Now, as linear polarization moves through magnetized plasma, it's transformed by effects that are sensitive to the density, temperature, and magnetic field. And the one that I'll be discussing today is Faraday rotation. That changes the orientation of the polarization plane as a function of wavelength. Now, that orientation is called the electric vector position angle, or EVPA, as I'll be referring to it later, sometimes also chi. And in this illustration from Wikipedia, we start off with this vertically oriented tick, and as it moves through this magnetized plasma in the pink cylinder, it gets rotated by some angle beta. And this depends on the plasma properties, also depends on the wavelength. It has a wavelength squared dependence. And so in order to try and pick out this effect, observers define the rotation measure, which is the slope if you are to plot the EVPA as a function of lambda squared, because again, this is a wavelength squared effect. And on the right here, I'm showing a plot from Kuo et al. 2014 for EHT target M87 star. This is older data from the SMA, and this is not resolving the accretion flow, of course. It also is sensitive to larger scale emission. But you can see they were able to measure EVPA as a function of wavelength, and they were able to put an upper limit on the RM here, less than 7.5 times 10 to the 5. You can see that the error bars are large enough that a straight line can't entirely be ruled out. RMs of that ballpark, 10 to the 5 to 6 radians per meter squared, have been measured in the millimeter for Sagittarius A as well as a handful of other similar systems, low luminosity AGN. And it's interesting because this can be related directly to the plasma properties via this equation under some assumptions. So let's take some time to break this down a little bit. You can tell by the units that RM is mostly used by galaxy people, but we can think about that for our accretion flows as well. So now first is this dependence on temperature. Basically what this is doing is suppressing Faraday rotation when the plasma becomes relativistically hot. It just gets less efficient at doing this. This is the electron number density, and then this is the magnetic field, and actually just the parallel component, the component that's parallel to the photon wave vector. And one thing to note there is that this is a signed quantity, so the sign of the RM could tell you about the direction of the magnetic field with respect to our viewing angle. But there's a major caveat or set of caveats here, which is that this equation implicitly assumes, as in that picture that I showed before, that the emission is a simple point source entirely behind this Faraday rotator. Whereas we think in these accretion flows that the emission and the Faraday rotation are co-spatial. So we'll be exploring to what extent this is actually true. In order to do so, in this study, we start off with 7 passing models from the Event Horizon Telescope collaboration paper. They're tabulated here on the left. They were chosen to explore both the MADs and the SANEs, and then in each of those categories, I bracketed the spins that were allowed according to the multi-wavelength constraints in that paper. And then for each of those combinations of magnetic field and spin, I bracketed the values of R high as well. And you can see what they look like in total intensity on the right here. I use the code IPOL, Moskibrodska and GAMI 2018 to do this ray tracing. I look at 11 snapshots typically, although I'll show you one with higher time resolution later as well, in order to get a handle on the time variability, as well as 5 different inclinations to see how that matters. And I also, of course, look as a function of wavelength in order to get that wavelength dependence. So let's start off with this one. This is one of the simpler ones. A MAD A equals plus 0.94, so highly rotating in prograde, and R high of 20. Here in this figure, the brightness of each pixel directly encodes the total intensity, whereas the color encodes the rotation measure, where large negative values are blue, large positive values are red. And so right off the bat, you can see that there's significant variation in the RM across this image, and it's even flipping sign. And so we're already not looking at this point source, and the RM is different in each of the pixels. If you weren't able to resolve this image, as is the case for, say, that SMA measurement that I showed before, the unresolved rotation measure that you get for this particular snapshot is written on the bottom left, negative value and a few times 10 to the 4. This is actually a movie. And so as we move forward in time, where time in days is shown on the top left, you can see significant time variability. This accretion flow is exhibiting a rotation measure on the bottom if it were unresolved. That's varying dramatically by orders of magnitude on timescales of just a few days, and also changing sign. So overall, we can see from this that the emission is definitely not a point source. The Faraday rotator is spatially complex as well. So we're going to need to interpret the rotation measure carefully. And then the unresolved RM is varying rapidly by orders of magnitude and can even flip sign. And this is because there really isn't a single RM for this image. What is perhaps more enlightening would be a distribution of all the RMs intensity weighted by how bright each pixel is. And that's what's shown here. for now each of the 7 models that I explored in this study. The one that I was showing you before happens to be this guy. Now, what I'm plotting here is essentially the RM distribution function spanning a very large range in RM. I've also taken the absolute value, going from a few times 10 to the 2 up to 10 to the 11. And there are a lot of features here that I'll walk through here. So first, there's this vertical line. To the right of this line, bandwidth depolarization in a single pixel is actually going to suppress the polarization by greater than 50%. That is, even across a small bandwidth here, 4 gigahertz, the EVPA is rotating so much that it's averaging the linear polarization down. I also split up the emission depending on where it came from, the front half versus the back half, compared to the midplane, and so that would be forward jet or versus counter jet for the SANEs, although the MADs aren't jet dominated. And what you can see from this is that there's often a significant difference between the emission coming from the forward jet versus that from the counter jet, especially in this very extreme model. Here we've got the counter jet emission almost entirely behind that dashed vertical line. That means that even though that accounts for intrinsically about half of the emission, it's actually going to be bandwidth depolarized to a smaller fraction of the overall linear polarization. Whereas the forward jet has a much smaller rotation measure, exhibiting something more like 10 to the 4. So you might be misleaded if, as we often do, you were to just integrate the total Faraday depth in this image, because it turns out that's mostly only affecting the counter jet here and not the forward jet. More on that. This is one of those interesting models, a large R-high SANE. They tend to have these cold midplanes. This one's a SANE A equals plus 0.94, R-high of 160. And this one's particularly interesting because the forward jet and counter jet emission looks significantly different. This is due to lensing. The counter jet is behind the black hole and so appears larger on the sky. And if you drill down deep into this one pixel that I circled in blue and look on the bottom, in this tracing, if you go from right to left, you're going towards the camera. The emission is in red, the rotation is in blue. You can see first there's all of this counterjet emission, but then it's behind this enormous cold midplane creating a large Faraday depth, and then the forward jet is basically dodging that. One thing I noticed is that this is so significant for this model that you get a different image if you look in linear polarization, not total intensity, linear polarization. If you do a single frequency image, as is often done, versus if you were to average properly over a 4 gigahertz bandwidth, that's shown on the right here. At a single frequency, the counterjet is dominating an image of linear polarized intensity, whereas that actually gets bandwidth depolarized, and over a 4 gigahertz bandwidth, it looks more like the forward jet instead. So since those distributions of RM are so complicated, again, we're breaking that assumption that we have a point source entirely behind the Faraday rotator. This wreaks havoc on the EVPA as a function of lambda squared. In the simple picture, you expect a straight line, and that slope is what you define as the RM. And that's actually the case for a couple of these here. These are the relatively low R-high MADs that are shown on the top right here. But others are much less linear. Ones with slightly more Faraday depth have some clear wiggles. And then the SANEs at the bottom, well, those are the ones that have a significant amount of emission, which would have a characteristic RM so large that you expect wiggles inside of a small bandwidth. Here's 226 to 230 gigahertz again. And so some of these SANEs are varying quite substantially. So the question is, can we actually measure this? This is entirely in theory land so far. I don't know what this would look like if you were to forward model this and put some observer error bars. If some of this gets eaten up by calibration, for example. But that would be an interesting direction to explore, to see if we can use nonlinearity in EVPA as a function of frequency to constrain models. One thing that the RM is often used for is to give you an estimate of the accretion rate. So if you remember that equation from before, RM as a function of temperature, density, and magnetic field, you can assume a simple analytic advection-dominated accretion flow model, and then you have a solution for what the temperature, density, and magnetic field should be, and then you can integrate that. And that's something that's been done in the past to set limits on black hole accretion rates. However, we find that the real picture is a lot more complicated. Here on the right, I'm plotting the absolute value of the RM as a function of accretion rate. And now I'm showing all of these models for 11 different snapshots. Each of the points of the same color are a different snapshot of the same model. Filled circles are positive RM, while negative RM is plotted with an open circle. So again, you can see this significant time variability and sign flips. They appear to be ubiquitous, both at 17 degrees, shown on the left, and at 90 degrees, shown on the right here. The upper limit from Kuo et al. Is shown as that horizontal dashed line, and all of them are capable of being under that limit at least sometimes. The simple analytic model is that blue region, and there's some wiggle room based on what you assume about the density profile. But overall, for a given accretion rate, such a model is overestimating the RM. The RMs get closer as you go to 90 degrees. And this is an inclination effect that is easy to understand just based on the geometry of these accretion flows. On the bottom left, I plot the characteristic radius at which Faraday rotation occurs, intensity weighted, as a function of inclination for all these models. You can see for low inclinations, less than 30 degrees, appropriate for our viewing angle for M87, for example, most of that Faraday rotation is happening very close in, so much less than even 10 RG. And then that just grows as you increase the inclination. It could actually grow farther than the y-axis shows here, 16. But we actually only integrated the radiative transfer equations out to 20M because that was where we were confident that the simulations were in inflow equilibrium. And it's interesting that despite integrating in such a small region, we're able to reproduce large rotation measures. In addition, that's often the opposite of what these models assume for the analytic models for RM as a function of accretion rate, where it's often posited that close in the electrons are going to be relativistic, and so that that temperature dependent suppression factor is going to prevent any RM. For example, in that Kuo paper, they assume that there's no rotation, that there's no Faraday rotation until 21 RG, when in fact it looks more like all of the Faraday rotation, at least in these models, occurs at lower radius. Here's a more detailed look at this inclination dependence. And for most of these models, if you look really closely, you can see a trend that the RM gets higher as the inclination increases. But this y-axis is spanning a very large range of values because the scatter is so large. Again, there might be more Faraday rotation outside of this domain, which might be important for interpreting sources, as I'll get back to later. But overall, we think it'd be useful to just continue monitoring such sources to get a better handle on the distribution of the RM and how much it varies over time, just so that we can test these models. A single snapshot is difficult to interpret. So more on that. This is the same movie that I showed you before. Oh, yes?
Just a 5-minute rough warning.
Okay. So this is the RM for that model as a function of time in days. And you could see that it is varying a lot and doesn't seem to care whether it is positive or negative. even though at least I expected that there should be a preferential sign just by the direction of the poloidal field. But that gray region is enclosing the 1 sigma region, and it's almost symmetric around 0. If you take an autocorrelation function of that, you see that it drops below 50% even between the time between snapshots, which is only 5M. Now, puzzlingly, Sagittarius star has exhibited a relatively stable RM, at least compared to this. It's maintained the same sign. So maybe that means that the dominant source of Faraday rotation is outside the simulation domain. And then on top of that, there's this variation occurring on much smaller scales. That's something that we should think about more. If you try and cross-correlate this with other properties, here is RM versus M dot, the linear polarization and the circular polarization. So you can see that even for a single accretion flow, RM does not trace the accretion rate. There is an anti-correlation between the RM and the linear polarization. That's expected. More Faraday rotation is going to cause more scrambling, so less linear polarization, and then also a greater amount of rotation measure. And no clear correlation with the circular here. That's circulars created by a separate process, Faraday conversion. Qualitatively, this matches what has been seen for Sagittarius star over the years, although this isn't an M87 model. All right, so I'll leave you with that. In conclusion, the Faraday rotation is co-spatial with the emission and non-uniform. And that the simple picture of a point source behind a single Faraday rotator is too simplistic. And that may mean that RM may not be able to straightforwardly give you an estimate of the accretion rate, but there is probably a lot of other information packed in there. And there could be interesting signatures in these 3 different dimensions. So in time, again, we expect different significant time variability and even sign flips. So repeated observations of sources can verify this. In frequency space, some of these models produce wiggles in the EVPA, also the linear polarization fraction as well, forgot to mention that, as a function of frequency, even for really small bandwidths. And so the question is this at an observable level? Can we constrain that? And spatially, the RM is typically quite non-uniform in a resolved image. So if one is able to spatially resolve the RM, there might be signatures there. There might also be signatures on, for example, long baselines in visibility space, something that we should explore. So thank you, and I'll take questions.
Thank you for that talk. So let's see, are there any? Yes, Jason has a question already.
Yeah, sorry, while others are thinking of questions. So I think it's this is great work. I think it's interesting to draw the comparison or distinction between M87 and Sagittarius star in this regard. These are like, Sagittarius star is probably the best studied source for this infer M dot from RM. And there, as you said, the RM is one-signed. It always has the same negative sign. It's pretty steady. The other thing I would point out is that the linear polarization fraction is high. So a lot of these confounding effects you discussed cause a lot of depolarization, right? You put the Faraday rotating material right in the emission and it's going to scramble everything. So I guess it's not clear to me that this is a bad estimate of M dot in Sagittarius star.
Okay.
Do you? I mean, no. I meant it as a question. What do you think? So I think a lot of what you discussed is M87 specific for obvious reasons.
Yeah, that is true.
But I guess what do you think could be the difference, or what? Yeah.
And well, I haven't tested models for Sagittarius star. I mean, it's not obvious to me that anything will be significantly different apart from timescales here. But as I mentioned before, the fact that the sign is stable, to me, well, my way of reasoning that is perhaps that there's more Faraday rotation on larger scales, an external screen on top of all of this, and then but the variability that would occur on event horizon scales, maybe that just isn't large enough to overcome the larger amount of RM coming from an external stream.
Is it true, like a sub question of that, is it true that the rotation measure in Sagittarius A star also displays much clearer lambda, like the EVPA versus lambda squared is much more clearly a line? Is that true?
I see that Jason's nodding. I'm not sure personally.
I think that would hint at the same thing, that you're not having this non-lambda squared dependence on the rotation measure, so it's probably happening at larger radii or something.
Mm-hmm.
Yeah, and also I don't know if any of the models are correct, but one of the interesting, amazing findings is that the RM and the M87 models is so close to the source, and that this is, Angelo, is your finding that this is a viewing inclination effect primarily? So that M87 is viewed pretty close to face on, and maybe that is just the the most confounding factor here, or something like that.
So yeah, the overestimate of RM as a function of accretion rate is definitely stronger for face-on inclinations, and at 90 degrees it gets closer, but still tends to overestimate. But then at the same time, I only integrate out to 20 M, so maybe there could be more.
All right. I guess Andrew has a question.
Yeah, hi. Thanks, Angelo. That was a really great talk. I just have two short questions. One is, do you think there's any sort of modification to these analytic models that I've used before, maybe to adapt them better to a face-on scenario that could make their predictions more in line with what we're seeing in GRMHD, or do you think the variability just sort of means that we can't use these models at all?
Well, and it seems to me pretty, I'm not sure how you would capture these random stochastic effects in an analytic model. Trying to include the inclination dependence would probably help, but I'm not sure how close to the truth you would get to that, how close to the GRMHD you could get with that.
Yeah, I guess you just seem to see things within some bound, even though it's something science, right? Like there's some upper limit in the magnitude of RM that maybe a simple model would help predict, and maybe that could be calibrated to GRMHD. I don't know, just a random idea.
Yeah, I haven't thought too much about it.
Yeah, I guess another question is looking at, from your experience looking at these images, like, and especially looking at the spatial structure of these reversals in RM and such, what do you think would be like the most interesting thing if we could observe resolved RM maps with EHT? What do you would there be obvious signs that you would be looking for? Would there be any sort of apparent things that would pop out in a resolved RM map that would distinguish between models or point to something interesting?
One thing that I see sometimes, but not all the time, is this. It's probably like here-ish. Streaks of negative right next to streaks of positive. And I think that has to do with the sign flip in the toroidal and radial components of the magnetic field across the midplane, also related to the, yeah, like right there, related to the formation of a current sheet there. That doesn't happen all the time. And the photon ring is probably going to be very messy in terms of its RM due to there just being multiple emitting zones, if you think of the zones on the geodesic as you keep crossing the emitting region.
Great, thank you.
Could you just go back to the Quo observations? I just want to stare at I forget what the difference in time scale between the measurements was.
Time scale and measurement?
Like they had like 4 data points or something. What was the?
Oh, those are. Oh, you mean, sorry. Yeah. That's a function of lambda squared, not time.
Oh, okay. So they only have one time measure. There's no. Okay. Hopefully they do they observe it, they estimate they measure the EVPA more often than Sagittarius A star, because I think it was like 15 years in between papers.
Oh gosh.
So one question I had is, should we be worried in our GRMHD simulations about the resolution? You know, if we have a low resolution, there's just a giant cell with a uniform magnetic field that we're using for these calculations. You know, or should we be worried that it's more twisted and there's more structure at smaller scales for this sort of thing?
That's
a big question. I don't know.
Yeah. I don't know. That's something I'm hoping to learn in this conference too.
Yeah, like maybe what would it look like in Bart's like 4 billion by 4 billion
Right,
simulations.
Yeah, if anyone's out there doing ultra high res, here's something to look at. You know, do you get convergence in this measurement?
Yeah, that would be very interesting. I think so. The hammer results that we have at this high resolution, they will be available through the EHT library. So this kind of analysis can be done on those simulations.
Great. Yeah, I would love to do that.
The other confounding factor that we've found is the outer boundary that Angelo alluded to, which is that if you really are looking through most of the mass, then at least in our longest duration simulations so far, that Faraday rotation is thought to peak out to hundreds of Rg, and we find that it peaks out at about 100. And since that's about the equilibrium radius in a very long simulation, it's not really clear if that's the answer or if it will continue to push out as you go further. So that's another confounding effect with polarization, is if you're not looking nearly face on, you really need to worry about the larger scales probably.
Right. Yeah. And this is just a test buried in the appendix of seeing what would happen if we integrated out to 50 M rather than 20. It seems that we're lucky for M87 that we're viewing it face on. For low inclination angles, the characteristic radius at which Faraday rotation occurs doesn't seem to change. May go out to larger values for higher inclinations, and you can see that trend on RM as a function of inclination as well. Although there's, again, so much scatter that it's almost within that.
All right. I guess, does Andrew, if you have something else to add? If your hand's still raised. Or maybe that's just still left there. All right. Well, I guess actually we're right on time to move on to the next talk. So thank you again, Angelo.